All right, we're going to try again to get this video lecture recorded. So we're going to talk today about molecular orbitals of conjugated pi systems, and we're going to show that the particle in a box is a reasonable model for the pi uh, bonds in these systems. So just to remind you what a conjugated pi system is, so we can talk about these conjugated dienes or conjugated polyenes, and they are just systems of alternating double and single bonds, typically in organic molecules. So this is an example of butadiene, which has got 4 carbon atoms and it's got 2 double bonds in this system. And so there's actually an extended set of pi orbitals across these 4 carbon atoms. In fact, there's 4 different pi orbitals, 2 bonding pi orbitals and 2 anti-bonding pi orbitals. And the way that we label these orbitals is basically from lowest to highest energy, where the lowest energy orbital has 0 nodes. The next highest energy orbital has 1 node. The first antibonding orbital has 2 nodes, and then the highest antibonding orbital has 3 nodes. So in fact, this ends up mimicking the particle in a box energy eigenstates. And so just to show that pictorially, you can see on this side, we have again the picture of those p orbitals contributing to the pi bonds. And in the 0 node case, basically all of those p orbitals are in phase. So there's constructive interference across the entire system of carbon atoms. And we can basically trace over that orbital with this function, which looks an awful lot like the ground state energy eigenfunction of the particle in a box. If we go up to the next pi orbital, so this is a pi orbital in which the first 2 p orbitals are in phase, and then p orbital 3 and 4 are in phase, but orbital 2 and 3 are out of phase with respect to each other. So there's actually a node right in the middle, one single node. And if we draw a curve over those orbitals, we end up with a curve that looks an awful lot like the first excited state of the particle in box system. We can keep going. So the psi 3, the first anti-bonding orbital, orbital 1 and 2 were out of phase, orbital 2 and 3 are in phase, and then orbital 3 and 4 are out of phase. So if we trace along that contour, we get this curve that looks like the second excited state of the particle in a box, and then all the way up here we've got all adjacent orbitals are out of phase, and if we trace over them we get a curve that looks like the third excited state, or psi 4, for the particle in a box. Okay, so that's, may just look like kind of a cute coincidence, but in fact, what also turns out to be the case is that you can do a reasonable job predicting the relative energies of these pi molecular orbitals from the particle in a box model. Okay. And so we'll see how that plays out in just a minute, but what I want to have you think about just right now is the fact that if we were to try to consider the energy levels associated with these different particle in a box states as molecular orbitals, and we asked, well, how many electrons are there to fill in those molecular orbitals? Well, for these conjugated pi systems, basically each carbon atom contributes 1 electron to the pi system. And so that means since there's 4 carbon atoms in the pi system, then there are 4 total electrons to distribute among these pi orbitals. Okay, so that means that we're going to fill up this orbital, which we're calling psi 1, and this orbital, which we're calling psi 2. Okay, so we're going to have 2 occupied fully occupied pi orbitals. And we're going to call this psi 2 the HOMO orbital, the highest occupied molecular orbital, and then psi 3 the first antibinding orbital. We'll call that the LUMO, the lowest unoccupied molecular orbital. Okay, and so of particular interest, because you can actually get an estimate of it experimentally, is the energy difference between the HOMO and the LUMO, sometimes called the HOMO-LUMO gap. So it's not precisely equal to the absorption energy of this system, but to a reasonable approximation, the HOMO-LUMO gap matches reasonably well with the absorption energy of this pi system that you might measure in a UV-Vis experiment. Okay, so let's see how we can do this. Okay, and so I just want to point out this is, in simple spirit, along with this idea of calculating the energetics of molecules from quantum mechanical principles. So this is a very, very rudimentary sort of quantum chemistry model for these conjugated pi systems. And of course, we've already, talked a little bit about some more sophisticated models, and we'll see some more of those in the near future. Okay. So let's think about actually applying this model to a system that we can study in the lab. So this is the molecule beta-carotene. This is a pigment molecule. It's what's responsible for making things like squash and pumpkins and carrots, of course, and many other vegetables, and even salmon, in fact, have an orange color. Okay, and so very common pigment molecule found in nature, and it is a huge conjugated, got a huge conjugated pi system. So in fact, there are 22 carbon atoms in this pi system. So that means there's going to be actually 11 occupied pi orbitals in this pi system, right? Because each carbon atom is going to contribute 1 electron. Each pi orbital can accommodate 2 electrons in total. So that means 22 divided by 2 is 11 occupied orbitals. So basically, we're going to have orbital 11 is going to be what we'll call our HOMO, and our LUMO is going to be orbital 12. Okay, and so our question is, all right, well, how do I estimate the energy difference between orbital 11 and orbital 12? And the answer is that we're going to use the particle in a box energy eigenvalues for this system. So if we're going to treat the electrons in this pi system as particle in a box electrons, then all we're going to do is ask a couple of questions. Number one, what is their quantum state that we're interested in? And we've already answered that. We're interested in 2 quantum states. The state n equals 11, which is the HOMO, and the state n equals 12, which is the LUMO. And then the other question we have to answer is, well, what is the length of the box? And so we're going to define the length of the box as basically the end-to-end distance of this conjugated pi system. So we're going to take the leftmost carbon atom involved in the conjugated pi system, which is right here, kind of on this left-hand 6-membered ring, and then the rightmost side of the conjugated pi system we'll call this carbon atom, also on the 6-membered ring. And so the length we can estimate by doing some trigonometry. If we remember that the carbon bond is something like 1.2 angstroms, you end up finding that the end-to-end distance is something like 20 angstroms. Okay, so reasonable approximation. So that's what we're going to use for L. So in essence, we need to evaluate 2 energy eigenvalues, right? One where n is equal to 11 and L is equal to 20 angstroms, and one where n is equal to 12 and L is equal to 20 angstroms. Okay. And the difference between those 2 energies is what we're going to be calling the HOMO-LUMO gap, right? So this delta E here. And so we can basically evaluate this prefactor here, right? this is Planck's constant. This is actually the normal Planck's constant, not reduced Planck's constant. We've written the energy of the particle in the box in terms of Planck's constant, not h bar. So we can evaluate this once we know what L is. We know what mass of the electron is. This ends up being 1.51 times 10 to the minus 20 joules. That's what this entire prefactor is. And then we just need to stick in our quantum numbers. All right, so 1.51 times 10 to the minus 20 joules times 12 squared minus 11 squared. So we end up getting 3.5 times 10 to the minus 19 joules. That's what we get as our estimate of the HOMO-LUMO gap. And if we actually measure the UV vis of beta carotene, okay, what we end up getting is that the absorption energy, which the absorption feature hits at about 450 nanometers, that means that the absorption energy is about 4.4 times 10 to the negative 19 joules. Okay, so that's actually reasonably close to the particle in a box estimate. It's actually within 20%. So, for a very simple model, that's not so bad. Okay, and so that's all to say that we can use this particle in a box model, which we've talked about extensively before, to estimate the energy eigenvalues and transition energies in conjugated pi systems. I just want to also spend a little bit more time discussing other features of the absorption of light by molecules and other materials. And so this is relevant for the previous discussion, obviously, because we're talking about inducing a transition between orbitals, typically stimulated by the absorption of light. Okay, and so why do molecules absorb light? And essentially, molecules absorb light because light can actually transfer energy to the charges involved in atoms and molecules. And of course, the charges are nothing more than the electrons and the protons. Okay, and so just to sort of try to give a picture of what light is, we often say this thing that light is an oscillating electromagnetic field. Well, what exactly does that mean? And so I really like this animation here on the left, and this shows what is meant by an oscillating electromagnetic field. And so in red here is actually the electric field associated with some light wave that happens to have a wavelength lambda. And so you can see actually there's this little arrow that's going up and down, and this is actually taking on, this arrow is basically following the instantaneous value of the electric field as a function of time if you're sitting in one particular point in space as a light wave is passing you at that point in space. And so by oscillating electromagnetic field, we basically mean that, it's this field whose magnitude is changing in time in a periodic way, right? So right now it's really strong and positive. Now it's zero. Now it's becoming strong and negative, going back to zero, going to strong and positive again, and back to zero, and so on. And it just does this, right? As long as the light field is passing, as long as you've got your flashlight or your laser pointer turned on, then you've got a field which is doing this. Okay, so now that's what the electric field is doing by itself, and when you put that in, when that electric field interacts with atoms or molecules, what happens is the electric field exerts a force on the charges, and that force is actually given by the charge of the particles that you're talking about multiplied by the electric field. So if you actually take charge and multiply it by the electric field, you end up with a force. Okay, and that's a nice statement of dimensionality. And so what happens because of that force is that the charged particles in your material are actually displaced. Okay, meaning if I look at this kind of glob of material, and this might actually be a reasonable model for an atom, or it might be a reasonable model for a nanoparticle or a molecule, is that basically at the points in time where the electric field is strong and positive, the force on the electrons is going to be pointing along the negative direction. So when the electric field is pointing up, the electrons are going to rush down. And they're going to leave behind the protons. And so that's going to create a displacement in charge where you have excess negative charge down here, excess positive charge up here, and that displacement of charge along some direction is called a dipole. So now, if the displacement of charge is associated with the transition from one energy eigenstate to another energy eigenstate, then the dipole moment associated with that transition is called a transition dipole moment. So in fact, this is a really important concept for the absorption of light. Okay, so basically the two conditions for a material absorbing light is, number one, the photons absorbed have to have energy to bridge the gap between some initial state and the final state involved in the transition. So we can denote the initial state psi I, so that's some initial energy eigenstate, and the final state psi F, that's some final energy eigenstate. And so in our previous example with beta carotene, psi I might have been psi 11, the HOMO in that material, and psi F would have been psi 12, the LUMO in that material. Okay, and so in that example, we saw that beta carotene absorbed light when specifically at colors that had energies matching the energetic gap between psi 11 and psi 12. So that's certainly an important criteria for light to have, but the other thing that has to happen is that there has to be a transition dipole moment associated with the transition between psi I and psi F. So that means that when you move your system from being in energy eigenstate psi I to the new energy eigenstate psi F, there actually has to be a displacement of charge associated with that transition. And that specific transition of charge is called the transition dipole moment. Okay, so basically it has to be non-zero in order for your material to absorb light. Okay, and so in fact you can actually calculate this transition dipole moment in quantum mechanics. It looks an awful lot like an expectation value, except for this is a very special kind of calculation where instead of having the same state in on the left and right terms of your expectation value expression, you have the initial energy eigenstate complex conjugate on the left side, and then your transition dipole operator acting upon your final energy eigenstate on the right-hand side. Okay, so that's kind of an important difference. So we typically write the values of the transition dipole moment with these two subscripts I, comma F. And I is basically going to be a quantum number associated with your initial state, and F is going to be a quantum number associated with your final state, and they'll denote basically which energy eigenstates go into this integral. And so if you want to practically calculate these transition dipole moments, of course you have to know what this operator looks like, what U hat looks like, what the transition dipole operator looks like. And in fact, for the particle in a box, in atomic units, and in atomic units, basically the charge of the electron is equal to -1. So the transition dipole operator for the particle in a box is basically the electron charge multiplied by the position operator. And so for the particle in a box, we call that position operator X. And then basically that means that the total transition dipole operator for the particle in a box is -X. So our actual integrals that allow us to compute the transition dipole moments between any two states in the particle in a box is just the integral from 0 to L of negative psi initial star times x times psi final dx. Okay, so that integral is basically something we can throw on Wolfram alpha, and it can tell us what the value will be. Okay. So remember we said that there has to be a displacement and charge associated with the transition for it to be, that transition to be excited by light. So another way of saying that is when we evaluate those transition dipole integrals, they are non-zero if those transitions can be excited by light. And if the transition dipole moment integrals are 0, then those specific transitions cannot be excited by light. So you can actually go on to Wolfram alpha using this expression that I wrote down here, where you're going to write psi I star is basically going to be square root of 2 over L, sine of I times pi times x over L, where I is some quantum number for the initial state, the x variable, and then square root of 2 over L sine f times pi times x over L, where f is some other quantum number. So you can try this, for example, with psi 1 and psi 3. You'll find that that's 0, so that means that light cannot excite a transition between the particle in a box state 1 and particle in a box state 3. You can try it with psi 6 and psi 8 and find that it's 0. And in fact, this is kind of a general rule for the particle in a box. It's not just like psi 1 and psi 3 are just magic states that can't be excited to each other through light. It's in fact all odd quantum number to odd quantum number transitions for the particle in a box are forbidden. Basically, their transition dipole integrals are 0. Similarly, all even to even state transitions are forbidden for the particle in a box. They cannot be excited by light. So even to odd and odd to even state transitions are typically allowed. You may find a few examples where they're not, but typically they are allowed transitions. Their transition dipole integrals are not 0. Okay, and so you can actually go into Wolfram alpha again, and you can compute the transition dipole moment associated with psi 11 to psi 12. What I actually want to do really quickly, just to throw one more animation up, is I actually want to animate this transition dipole integrand as a function of time. So not the integral itself, but the transition dipole integrand. So this function psi I star x times psi f, where psi I is psi 11 and psi f is psi 12. So that would be basically the HOMO LUMO times transition dipole operator for the particle in a box. Okay, and I just want to run an animation of this using Python. So basically here I have psi, what I'm calling psi 1, that's in fact psi 11, because I'm basically calling my particle in the box function with quantum number initial being 11, quantum number final being 12. So I'm basically going to generate psi 11 times x times psi 12 right here, and I'm going to be including both the spatial and the time components of that psi 11 and psi 12 function. So that's going to allow this thing to move in time. So I'm going to hit play, and we're going to bring up the animation. And so what you can see is that this, this function, psi 11 times x times psi 12, or put another way, psi 11 times the transition dipole operator times psi 12, actually oscillates in time. And so what that signifies is that the charge density is moving around in time. And so for this particular system, you can imagine the appropriate way to excite it with light is to have the electric field oscillating back and forth along the pi system. And what that's going to do is tend to move charge to the right-hand side in one period of the oscillation and then back to the left-hand side of the other part of the oscillation. And so, in fact, you can imagine the electrons basically sloshing back and forth from one side of the pi system to the other, and that's basically what's signified by this animation. You can see over here now there's a lot of charge on the right-hand side. Now there's a lot of charge on the left-hand side, and back to the right-hand side, and so on. So those are basically the charge density oscillations that this system experiences as a function of time as it interacts with light. Okay. Well, thank you for your patience in me getting up the replacement video for this, and I hope it was helpful. Let me know if there are any